What if I told you that a raindrop could cause serious damage during high-speed flight? At over 800 miles per hour, even something as small as a raindrop can hit with enough force to weaken a jet's radome. So what is a radome? A radome is a protective nose cone that shields radar and sensitive electronics. During combat or in high-speed flight, that's the difference between mission success and mission failure.
That's why our team set out to solve a crucial problem. How do we simulate and study these impacts in a controlled and cost-effective way?
Our solution to this problem is RITA, a radome impingement test apparatus. My name is Ryan Ramston, and I'm the team lead of this project.
My name's Hunter Gray, and I'm the procurement lead on the team.
I'm Tanner Linson, and I'm the mechanical engineer of the project.
I'm Owen Sutherland. I'm an aerospace engineer.
I'm Hank Erickson, and I'm an aerospace engineer.
I'm Tyler Fleming. I'm an aerospace engineer.
My name's Luke Garman, and I do applied physics.
Our project aims to create a cost-effective testing apparatus and methodology to evaluate damage to radomes caused by simulated high-speed water droplet impacts. This will serve as a way for future researchers to test radome samples and simulate raindrop collisions at any speed to account for any flight condition. Current impingement methods involve a rocket sled approach, which mounts a radome sample onto a sled on rails. A rocket on the back of the sled accelerates the sample through a sprinkler field to simulate rain particles impinging the radome. Later, the radome is removed and analyzed after the test.
With this project, our sponsors at Raytheon were most concerned with the system's safety, performance, repeatability, and accuracy. RITA is a helium-powered single-stage light gas gun. This is our manifold enclosure. It is used to cover our manifold for safety reasons. Our helium tank is connected to a regulator, which is used to control the amount of pressure we feed into the system through this hose. Our pressure vessel and manifold are used to contain the pressure of the system. Our electronic pressure release can be used to release pressure from the system if we ever want to reduce pressure in the system, or in case of an emergency. Our pressure transducer is used to read the pressure in the system at any time. Our blow-off valve is used to release pressure in the system automatically once a certain pressure is reached. It is currently set at 750 psi. Our manual release is a backup to the electronic release. If something were to go wrong with the electronic systems, it can be used to release pressure in the system. This is our firing actuator. This is what is used to actually fire the system. It opens to allow pressure to flow from the pressure vessel and manifold through the barrel, which propels the bead into the radome. Our vacuum actuator can be used to control the vacuum.
One of the most important challenges for this project is actually accelerating a bead to the speed of sound, which is around 343 meters per second. While last year's system provided an excellent starting point for a firing system, it only used air, and due to the nature of the shock waves, the velocity of the bead projectile ended up being limited. Our first thought was to accelerate the air directly, which involved designing and manufacturing a converging diverging nozzle, which is an aerospace structure that forces air to move faster. And this nozzle, theoretically, will accelerate subsonic speeds up to supersonic speeds.
Once we began testing it, we actually found that there was a significant decrease in the bead velocity, which did not support our initial findings. As a result of the failure of the nozzle, we switched our design to use helium as the working gas. Helium works to accelerate the flow to supersonic speeds as it has a much lower density than air, which increases the local speed of sound to roughly 3 times that of air.
As an additional improvement, we created a vacuum system. This suctions out the air, maximizing the helium in the vessel. This improves the helium to air ratio, further increasing the bead velocity. We were able to achieve a good seal that does not affect bead velocities using a sheet of paper held in place by a hose clamp.
We decided to rework the stand that our manifold was mounted on. Last year, they just used a simple store-bought sawhorse design. We used 16th-inch steel. We did some analysis. We found that this was sufficient enough to withstand any penetration from our heaviest valve possibly blowing off under 500 psi.
Here's the mount we designed to hold our radome samples. It's fully articulatable both rotationally and translationally. It's made of welded steel, 3D printed parts, and it can hold up to a 33 by 33 centimeter diametral or square radome sample. So as you can see, here's our total envelope.
At the heart of the system, we have the electronics and the software. RITA has been updated to be controlled via a Raspberry Pi and a touchscreen GUI.
RITA is equipped with an advanced method to quantifiably assess material damage to help engineers determine whether or not the material will be feasible for radome application. As you can see, this sample took a bit of damage, but how much exactly? The damage scoring matrix allows us to answer that question on a scale from 0 to 100. 0% meaning the sample is undamaged, while 100 means the sample is completely destroyed. There are 4 main factors that weigh into the final damage score: critical fracture toughness, coating damage, water resistance, and the damage mode. Each category aims to quantify test sample damage while also allowing the user to fully customize weights to determine the scores that they find most important.
Since we can't shoot actual water droplets, several academic papers suggest that polymeric materials like nylon can serve as a fantastic substitute in place for actual water droplets. This is due to the similar density and bulk modulus shared by both water and nylon. In other words, nylon is the closest solid material to water.
Because one is a solid and the other is a liquid, we needed to develop a conversion factor between the two. Understanding the physics behind a raindrop impact is critical for this. A force-based approach was then attempted and verified. These graphs show the pressure distribution over time for a 4 millimeter raindrop impinged at 500 meters per second. The one on the left is from an academic paper, and the one on the right is our replicated results. This graph on the bottom, which essentially shows us what the maximum force will be for a raindrop traveling at a certain speed and for a raindrop of a certain size. And this seems to be the first of its kind in academia. We then need to find the equivalent nylon impact force delivered by a 6 millimeter nylon bead. So our original idea into doing this was to use the conservation of momentum and use slow motion camera footage of a frame rate of around 100,000 frames per second in order to actually find the impact time, which would give us the impact force. This will bridge the gap between a solid and a liquid.
Rita was required to fire at velocities from 50 meters per second to 343 meters per second, or Mach 1. Last year, they fell just short of achieving this, hitting 303 meters per second. With our improvements this year, Rita was able to achieve speeds of above Mach 1.5. Rita additionally has a very high accuracy and is able to place a bead within 3 millimeters of the target location on the radome. The articulating mount is also able to translate in order to change the impact location to any point along one axis of the radome, and rotate to achieve various impact angles on that point. It can hold circular samples with diameters of up to 30 centimeters, or square samples with sides of 30 centimeters.
While the more expensive rocket, sled, and flight tests will continue to be utilized for impingement testing, Rita allows us to bridge the gap between preliminary analysis and these expensive methods.
This system, along with our damage scoring matrix and raindrop modeling, allows Rita to be highly effective as a preliminary testing method. It's easy to use, it's portable, it's repeatable and accurate, all while maintaining supersonic speeds. Rita offers a cost-effective and efficient way to simulate high-speed rain impacts on radomes, making a promising solution for future material testing.
It's been an absolute blast working on Rita. We would like to give a big thanks to Raytheon for sponsoring our project, and we look forward to continuing to see the development of Rita and its applications in defense and technology.